So, hello guys, this is the second video for laboratory number 12. Let's go over it. So this is the recitation guide. I would like to start really quick with the first exercise. They are telling me that I have 2.020 grams of potassium chloride, which is getting dissolved in 100 ml of water. They are telling me that the change in temperature dropped from 25 to 23.9 degrees Celsius. They are showing me in this case the stoichiometry for my reaction, which you will see that matters. And they are starting asking me a few questions. This is going to be the useful information for this exercise. Whoop, how that happened? I don't know. Okay, coming back here. This is the useful information you guys need to know. Let's start. Delta T, I don't have to explain that, but you need to know that delta T is always going to be expressed by the change in temperature, so you need to consider that the final temperature goes first, and this is a subtraction. So final temperature minus initial temperature. Second, what is the total mass for the solution in grams? In this case, you need to consider that they are telling you that the density of that solution is going to be around 1.00 grams per mil. And therefore, after that, you can make the calculation. If you have any questions, just pause the video and take a look at it. Third, what is the K surroundings in kilojoules? Okay, so if you recall from the previous video or from your lecture, you will recall that this is the equation you will be using at all times, where K, which is the K surroundings or the heat exchange that you have between the system and the surroundings, equals mass, which is going to be expressed in grams, times C, which is the specific heat capacity. They are giving you that information up here. The specific heat of the dilute aqueous solution is approximately 4.18, so you have that information already beforehand, and the delta T, which we already have it. Okay, I'm showing you here what you guys should have, and then I'm just performing the calculation. Quite straightforward. In the end, you should get something like this. If you don't get it, check your results. Check that you need to cancel grams with grams, Celsius with Celsius degrees. So in the end, your final expression should be energy. Of course, I got my energy here, but they are asking me to express that energy in kilojoules, and therefore I make the conversion. I won't go into those details. And if this is the K for my system, for my surrounding, sorry, and as I told you, my K of the surroundings, it's gonna equal minus my K of my system, and vice versa. So you need to keep this in consideration, because if you have a reaction going on, and that reaction, in this case, they are telling me that my reaction is winning energy, that energy has to come from somewhere, right? That somewhere is the surroundings. So my system, it's gonna be winning energy, and my surroundings are gonna be, in this case, losing that energy. That's the balance we need to consider according to thermodynamics, okay? Moving forward, they are asking me what is the amount of potassium chloride reacting, in this case, in moles. You guys already know how to make this, how to get this done. I just did it because I need it for the upcoming exercise, but I won't go into those details. What is the delta H of the system? So this is asking you, in this case, to find the delta H per moles. Okay, so this is going to be specific to the amount of moles you guys expressed over here. So you need to calculate the KCl moles. Okay, I got these results. So I got that I have 0.02710 moles of potassium chloride, which means that if I already calculated my K of my system to be 0.47 kilojoules, I just need to divide that over the amount of moles I got for my reaction, and that's going to give you, in this case, the delta H of the system. Number 7 is telling me that is the dissolution of potassium chloride an endothermic or exothermic reaction? Is a question. Well, once again, in this case, we need to consider what's endothermic and what's exothermic, and actually that's something I would like to explain in this video. So, once again, let me just make this drawing here. If I am cooking, I have my pot over here. That should be a pot. And this pot has my mixture. Let's say I have in this case water and rice. I'm trying to cook rice, right? You know that this is not just gonna be cooked by itself. You need for this to be done, to get done, heat, right? External heat. And that's the energy you will be applying to your system in order for it to get your rice done. And that heat means that in this case, this is going to be representing your surroundings, and your rice is going to be representing your system. So what's going on in here? Let's think of it. Your surroundings are losing energy because you are applying that energy to your pot with your food, right? Therefore, we should let me just change the colors. We should expect that my surroundings, and I'm going to express that as delta H sub S, should be losing energy, and the delta H for my system, it's gonna be winning that energy. Do you see it? When this is going on, when this happens, we normally say or refer this as an endothermic reaction. And this endothermic reaction will always have a delta H with endo winning a positive sign. Okay? Conversely, and now let's just talk about an exothermic reaction. Let's say that I have my beaker or my Erlenmeyer in this case, and in this Erlenmeyer I have TNT. Trinitrotoluene, okay? A very known and very potent explosive. What happens if this explosive reacts with water? Whoops, that's not the color I wanted. If this reactant reacts with water or with moisture, which is the same, in this case, this is gonna make this TNT explode. What that means? That means that this TNT will have a very violent reaction where it will start liberating energy to the surroundings. And consider that therefore this is gonna be my system. Okay, so in this case, let's take a look at it from the perspective. The delta H for the system, which is the delta H I care about, in this case is gonna be negative because the system is losing that energy, and that energy therefore is getting passed to the surroundings because those surroundings are winning all that heat. Okay? And therefore we call this an exothermic reaction. And this exothermic reaction is getting characterized because it has a delta H. Sorry, I made a mistake here. That is always gonna be negative because we are looking at it from the perspective of the system. Same case here. I hope this helps, guys. Okay. So moving forward, this is the very same explanation I'm showing you here. Take a look at it, and if you have any questions, please let me know. Okay, so now what will happen to the answers from question number 1 to 5 and 7 if the amount of KCl dissolved in water is doubled? Well, regarding the first questions, that means that if you double the amount of water, you will double the mass, therefore you will double the moles, therefore you will be doubling the delta H's. Okay? Of course, regarding this question over here, the signs won't change whatsoever, so you won't change that. You only will change the magnitudes of the delta H's or the case you have in your result. Question number 9, it's for you to do, so this is yours. Moving forward. Question number 10, if a hot piece of metal is placed in a coffee cup calorimeter and the water absorbed, in this case they are telling me 600.0 joules of energy, how many joules of energy did the piece of metal release? And this is a good question. If you think of it, they are telling me in this case that I have a piece of metal and that this piece of metal was placed in a coffee calorimeter just as the one you saw in the first video. I'm probing here the temperature, so this is my thermometer, and they are telling me that the water in this case surrounding that piece of metal, so this water surrounding the piece of metal, 1,600 joules. That can only mean that in this case, the metal itself is releasing that energy to the environment, which in this case is that water. And that therefore means that this piece of metal has to be losing that same amount of energy the water is winning. Therefore, minus 600 joules. It has to be just changing the sign. So this is a very good example to point out the necessity for you guys to understand how the sign matters. And as you can see, it does. Moving forward, question 11 is going to be for you. Take as the example the soils example I just point out. By the way, that example it's available in the slides from Dr. Wei presentation. 12. How many energy is released to raise the temperature of 50 liters of water from 25 to 85 degrees Celsius? First of all, note that in this case, the temperature is getting raised. So that means that in this case, my system is winning energy. If my system is winning energy, what that means in terms of enthalpy? Is it getting an endothermic or an exothermic reaction? What do you guys think? It should be endothermic, right? Well, moving forward with this. So I just, in this case, change from 50 liters of water to milliliters because that's what I need. So I can use this value for the density they are giving me here. Remember that I'm just changing here from volume to mass because I need to make that change. Once I make that change, I need to know my delta T. This is supposed to be a delta. So you understand that change in this case is telling me that I have a delta T of 60 degrees Celsius with a positive sign. And once I go to calculate my K, I just make all the math, and in the end, you should get this value. And as you can see, that has a positive sign, which means that in this case, I should be dealing with an endothermic reaction. Number 13. If 205.0 joules of energy are applied to 5.000 grams. Now I know why this exercise is wrong. Okay. Grams piece of iron at 25 degrees Celsius, what will be the final temperature of the iron? The specific heat of iron is 0.444 joules per grams degrees Celsius. Okay, so they are telling me that I have my K, I have my mass, I have my initial temperature, and the question is for us to get or to recover what's the final temperature. Now, if we go to the equation, we know that K equals mc times delta T, which equals mc times the final temperature minus the initial temperature. And this is the variable I want to find. So I just need in this case to solve for T sub f, and in the end I should get the right value. And by the way, just making the correction here because I just made a mistake for this exercise. If you look at it in the end, you should have, oops, that K it's gonna equal 205.0 joules over m times C, so that's gonna be 5.000 grams times my C, which in this case it's 0.444 joules grams Celsius, close this parenthesis, plus my initial temperature, which is 25.00. If you take a look at the units, joules cancels out with joules, in grams will cancel out with grams, and your final expression should be in degrees Celsius, which is what you care about. Take a look at the math of it and let me know what you guys get. Moving forward, 14, if 347.0 joules of energy are applied to a piece of gold of an unknown mass, take a look at this, and the temperature increases from 25 to 50, what is the mass of the gold sample? And they are telling you here the specific heat of the gold. So the same thing, you just need to, in this case, to solve for what they are asking you to get, which is the mass. I already did it for you, but I won't do the math, so please take a look at it and do it yourself. Exercise 15, methane undergoes combustion to produce carbon dioxide and water. And the question is how many kilojoules are released when 42.0 grams of methane are burned. And they are giving you here the reaction. So they are asking you about methane. And here, stoichiometry matters. For this specific exercise, not that much because in this case you have a 1-to-1 ratio between the delta H and the reactant you care about. However, and I already did it, you take a look at the math, you will see that it's quite simple to do it. However, if you go to exercise 16, now they are asking you about the reaction of methanol, which is used as a cooking fuel. And this undergoes a combustion to produce carbon dioxide and water as well. So it's a classic combustion reaction as those you have seen so far. And the question is, how many kilojoules are released when 3.25 moles of methanol are burnt? However, if you look at this reaction, the stoichiometry will matter because you have 2 moles. So this represents a 2-to-1 ratio. So here, the stoichiometry of the reaction matters because it is not a 1-to-1 ratio anymore. What that means is that you have those 3.25 moles of methanol, and you need to consider that per each 2 moles of that methanol, you just have 1 mole of the reaction per se. And then you can make the conversion to 1 mole of the reaction, which is going to be related to, let me change colors here. Actually, let me use this one, the enthalpy of that reaction. And in the end, you should get something like this. The gas tank in your new car can hold 60 liters of octane, which has a density of 0.72. So they are giving you volume, they are giving you densities. You can see that it's pretty much the same. And they are giving you, in this case, the reaction, but good for you. This is going to be, once again, a 1-to-1 ratio. Therefore, you just have to go really quick to the conversion. As you can see in this case, I just converted real quick from 60 liters to milliliters, and then I just made the whole conversion. Take a look at this and let me know if you get the same value. And you will be doing number B or exercise B, better say, because it's basically the same. For the exam prep exercises, you will be doing 18 and 19. I recommend you guys to do it because these are very like to those I already discussed above, and this is going to help you to understand what's going on when we are dealing with energy and heat exchange. Okay? By the way, you always will have all the selected answers, which for this guide are all the answers basically, so keep that in mind as well. I hope this helps. Please let me know if you have any further questions. And this is the last video, so it's been a pleasure to be your teacher throughout this semester, guys. Even though we had this very odd situation, um, I appreciate the time you gave me, and it's been a good semester. So I hope you guys have enjoyed as much as I did. Bye bye.